Hello everyone and welcome to my Zoom cave. The map behind me is a reproduction of arguably the first geological map that was ever made about 200 years ago. A lot of what we do in teaching geology programs in the second year is about geological maps, and particularly about how to interpret what's beneath the Earth's surface based on a geological map. Now, in the old days, that would be done by beautifully crafted wooden models like this, where you can look at the map view and then you can turn it around to see what's inside. And what I want to do in this talk is to take you on a journey. There are not going to be any very clear conclusions because COVID has thrown everybody for a loop in this process. So we have been inventing things on the fly. So I want to take you through some of the stages in that process. So the essential problem we face is that our observations are mostly made at the Earth's surface. And the Earth is opaque. We can't see inside. And visualizing what's inside is hard if we don't have a handy wooden model, or if we're not working in a beautiful area like this, which is a place we can't easily take our students. This is in the front ranges of the Rocky Mountains near Exshore. And here I think you can visualize that layers are sloping down into the ground. And you may be able even to visualize that if we were to draw a cross-section through this landscape, it would look something like this. And this is from a published geological map of the same area, showing how those layers go down inside the ground. Now, going from a map to the layout of the rocks within the Earth involves a number of steps. And a couple of techniques are commonly used in teaching geology. And both of them have a bit of a reputation amongst students of being abstruse and difficult. And the first of those is to make what are called structure contour maps. And I can show you on the visual presenter how we go about doing that. So effectively, we draw lines through points on the geological surfaces that have a constant elevation. And by doing that, we can get an idea of how those surfaces are positioned and how they are oriented. This is a simple map exercise that we use. This is a complicated one. Those are what has traditionally been used to teach geology students to interpret the interior of the Earth. A second technique we use is for measuring angles in 3 dimensions, because it's also a common problem to have to measure the angles between two randomly oriented things in 3 dimensions. So that's not something that you can use a simple protractor for, and we have a kind of a 3-dimensional protractor called a stereographic projection. And again, a stereographic projection is regarded as a bit challenging traditionally by geology students. So for many years, we addressed these techniques by means of a book of lab exercises that we sold through the university bookstore to the students when they started taking a second-year course on geologic structures. Over the years, we added more and more material to that. So the students started asking, well, why do we have to buy a textbook as well? Everything here is in this manual. So we ran with that idea and produced an open educational resource, which is now a free textbook that the students can download and print for themselves. And it contains both the theory content and all of the lab exercises. So we were more or less just into our first incarnation of using that when COVID struck, and we had to pivot rather rapidly in order to continue using it. A second innovation that we adopted was a 3D printing project, and this is a TLEAF supported project to help the visualization of some of these map problems by using 3D printed models like the one you see here. So I'm going to take you through the workflow of making these, and these models have been pioneered by my postdoc, Mary Lee Reynolds, who's co-author on this talk. She's now working for the Northwest Territories government as a government geologist full-time. So just to take you through the workflow of making these models, here's that map structure contour map from the Open Educational Resource. And what Marilee did was she used a software called Leapfrog. And Leapfrog is widely used in the mineral exploration industry, which is the subject of Marilee's PhD. It's quite technical, but it is a good program for building three-dimensional geological models of structures, and that is actually what it's widely used for in the mineral exploration and mining industry. So this illustrates her workflow for building 3D printed models. So from Leapfrog, the 3D model was exported into a software called Fusion 360, which is widely used for making 3D printed models. And we did a few things. We need to hold the model together, so we included some hollows for magnets. And here is the model being built in the engineering garage. It lays down layers of plastic to gradually build the parts of the model. And this is a speeded up image. It takes several hours to produce each piece of the model. So then we install magnets and we apply whiteboard paper to some of the surfaces so that we can work on the surfaces. And we can replicate in 3D the structure contour process that the students find so abstract when they carry it out in 2 dimensions. Now, there are some things we discovered as we were building the model. A map that works very well on paper may not work super well when it's printed in 3D. So this particular model came apart because we had left a piece that was very thin, which we didn't realize. So we actually redesigned the model, and we have a better version ready to go now. So finally, once we've adjusted the model, we actually reproduce a new geologic map in Illustrator. In this case, we just extended it to the east a little bit so that it would not fall apart so easily. Now, one sideline of the Leapfrog process is that you can view your model in a software called Sequent View. And Sequent View, it turns out to be quite a powerful teaching tool in itself, because you can spin the model around on the screen and you can actually make slices through the model. Now, Sequent View is actually part of another program that we have used, which is a program called Visible Geology, which has a helpful module for visualizing the stereographic projection, and that one is shown here too. So we were midway through designing 3D printed models, and then COVID struck. So we had some quick decisions to make. We discovered that few of our students had scanners that would allow them to send their completed maps to us. And really scanning a map with your phone is not good enough for the standards that we work to. We want to be able to measure the students' maps, make sure they've done them accurately, and phone scans just really don't cut it. And worse still, some students don't have printers. And of course, we had created a problem for ourselves with the Open Educational Resource, because in the old days, they would have all had a paper copy of all the lab exercises, but many of them hadn't printed many of them yet, the ones we hadn't got to. So we had to discover how to deliver all of these exercises to the students and how to get them back from the students so that we could mark them if we were going to use them at all. So following the suggestion of one of the TAs, we explored doing these exercises in PowerPoint instead of on paper. And I had always been a bit negative about PowerPoint as a drafting tool. It's certainly not as sophisticated as CorelDRAW or Adobe Illustrator, but it has a couple of advantages. One of them is that the students will have free access to PowerPoint. And the other one is that it's simpler to use than a professional drafting program in most ways. So the learning curve is not as steep, and the students, if they've played with PowerPoint at all, have some idea at least of how it works. So we discovered that we could actually move our paper exercises into PowerPoint, and the students could complete them in PowerPoint by drawing structure contours as shown here on PowerPoint diagrams. And you have to take certain steps to make this work well. And I actually prepared a small tutorial for my colleagues, I'm happy to share it, on how to make a paper exercise work well in PowerPoint. You need to lock some things down so the students can't accidentally move them, for example. We also discovered that the stereographic projection exercises could be moved into PowerPoint. And in some ways, these actually work better in PowerPoint than they do using tracing paper and the traditional methods. And one of the reasons for that is because using the traditional methods, it's very difficult to turn the 3D protractor around while you keep your projection on your tracing paper stationary. And so the students have constant frame of reference battles because north gets turned around in all different directions. Now, in PowerPoint, you can turn the net around while you keep your projection stationary. So north is always at the top, and your protractor turns around. So conceptually, it's easier. And I'm pretty convinced that the students this year, when we did everything in PowerPoint, actually had an easier time of the stereographic projection than they did doing it the old way. So I don't think we'll go back when COVID is over. So I felt that was so successful that in the first few weeks of the pandemic, I wanted to get the message out to my colleagues in other institutions. So I prepared a series of YouTube tutorials. There are 11 of them going through all of the common operations on the stereographic projection. And I made those available to mailing lists, one in Canada, a structural geologist, and one a global mailing list of structural geologists. And I have a YouTube channel now. I have 148 subscribers, as you see here. And I have well over 7,000, nearly 8,000 views of these little tutorials on how to do things on the stereographic projection. Most of them are only 2 or 3 minutes long, which for something commonly regarded as obscure and technical, I think is pretty good going in outreach terms. So we have made some attempts to distribute this technique around the world, and a number of people have indicated that they're going to use it going forwards. Another thing we did, I haven't mentioned real rocks in these labs, but we do have quite a lot of rock samples that we show the students. And we have made 3D models of those too. You have to take about 100 photographs from all different directions with a good camera. And then we use a program called Agisoft Metashape to build a 3-dimensional model. And then for distributing this to the students, we can use the platform Sketchfab, which allows you to upload your own models and deliver them to the students. And quite a lot of our hand samples that we have used in this class, we've distributed in this way. So these two programs, SequentView and Sketchfab, provide a fluidity of manipulation. They allow you to spin things around that's quite close. It doesn't substitute for hands-on, but it's actually quite close to the hands-on experience. And so this has been an interesting discovery for us, and they've been quite well received by the students. So after COVID, we will probably not go back to the old ways in all areas. For the stereographic projection, we'll probably never go back to paper. If we can get computers in the classroom, that's the way we'll do it. For the map work, if we can eventually get back into the 3D printers, we can build the 3D built models, and we can actually provide the 3D models and the on-screen version to the students. And maybe we can do some surveys to find out which they like best. Maybe we can in some way compare their results with each method. So hopefully we can get some analysis done as to how well these methods work. For hand samples, well, yes, hands-on with real rocks is still the best. But if we have remote students who can't get here in the fall, we will probably still use the Sketchfab models. So I want to thank the University of Alberta Teaching and Learning Enhancement Fund, particularly for allowing me to pivot to different things. Obviously, it became impossible to 3D print anything once the pandemic set in. But we think we've discovered some neat things with the on-screen digital models, which are surprisingly effective. I want to thank the libraries for their support of the Open Educational Resource, and these teaching assistants in EAS 233 who did an amazing job of helping with the building of digital models and teaching the students how to do things in PowerPoint that they had no idea they could do, having only used pencil and paper before. And I want to thank the students as well. Thank you for listening.